from the properties of Laplace transform, another property is shifting property. This shifting property is again two types. One is called first shifting property or frequency shifting property, and another is second shifting property or time shifting property. So first of all, we will go through the time shifting property. So time shifting property, time shifting property, it is also called as second shifting property. Second shifting property. See, the shifting operation explains the complete signal is shifted either left side or right side. So two types of shifting operations are there. One is a left side shifting operation and another is right side shifting operation. That is called advanced signals and delayed version of the signal. See, Laplace transform of f of t. Laplace transform of f of t, now I am writing in terms of f of s. So we can write either x of t or f of t. F and x explains the name of the function. So Laplace transform of f of t is f of s. The time domain is converted into frequency domain. If the shifting applies in time domain, that means Laplace transform of f of t plus or minus t naught. Here t naught is constant value, t naught is some constant value. Algebraic summation of some constant with time is called time shifting property, or it is also called as second shifting property. So whenever the shifting applies in time domain, in frequency domain, this f of s function, f of x function multiplies with a exponential signal. That exponential signal is e to the power of plus or minus s t naught. Because here this time domain signal is t naught time shifted, and in frequency domain this complete function multiplies with exponential function, that is plus or minus t naught times here. So exponential shifting operation explains the phase shifting. One side shifting operation and another side it gives the phase shift operation. So Laplace transform of f of t plus or minus t naught is e to the power of plus or minus s t naught into f of s. This is the standard statement of time shifting property or second shifting property. Now we have to prove this one. So first of all, I am writing Laplace transform basic function here, basic formula. Laplace transform of f of t is f of s. Laplace transform of f of t is f of s. The f of s equation explains integration is from minus infinity to plus infinity. The given function is here f of t into e to the power of minus st dt. Right? Laplace transform of f of t is f of s, that is equal to integration from minus infinity to plus infinity. The given time domain function is here f of t function, f of t into e to the power of minus st dt. This is the basic Laplace transform formula. Now here from this we have to prove this equation. Laplace transform of f of t plus or minus t naught is e to the power of plus or minus st naught into f of s. To prove that purpose, first of all I am taking here LHS equation, left hand side equation. Here LHS equation is Laplace transform of f of t plus or minus t naught. Now we have to write the Laplace transform of this function. See, here I have wrote one simple formula here. Laplace transform of f of t is integration from minus infinity to plus infinity. Write this function as it is here into e to the power of minus st dt. From that, directly I am writing now here integration from minus infinity to plus infinity. The integration is from minus infinity to plus infinity. What is the given function here? F of t plus or minus t naught. This is the given function. Write the given function as it is into e to the power of minus st dt. Right? So the given function multiplies with e to the power of minus st, and again we have to apply integration with respect to t. This is the basic Laplace transform equation. Now here I have applied this Laplace transform of this signal here, f of t plus or minus t naught. Now just observe this equation. In this equation the integration is with respect to t is defined, but the function is defined in terms of t plus or minus t naught. So t naught is constant, right? but the function is defined in terms of t plus or minus t naught, but the integration operation is with respect to t is there, so we have to equate these two. So to equate these two purpose, here I am assuming this analysis here like this, t plus or minus t naught is equal to some other variable I am taking now, the variable is u. We can assume any one variable, right? So t plus or minus t naught is equal to u, then t becomes here. Take this t naught this side, then becomes u minus r plus t naught. See, plus or minus becomes here minus r plus t naught is constant, write this constant as it is here. So if it replaces this part, again we have to replace this one also, right? So this becomes now differentiate both sides this side, then it gives the dt is equal to du because t naught is a constant, right? So now we have to replace this complete analysis in this equation, and integration operation limits are same here because here t is infinity, u is also infinity. If t is minus infinity, u limits also changes from minus infinity to plus infinity. So minus infinity to plus infinity, right? Now I want to apply these complete limits in this equation. I want to substitute this in this equation. Then this side it becomes like this, Laplace transform of f of t plus or minus t naught is equal to Laplace transform of f of t plus or minus t naught is equal to, so integration minus infinity to plus infinity, this part I am writing as this, and here t plus or minus t naught becomes u. So this function becomes here f of u into e to the power of minus st is there. What is t here? U minus r plus t naught. Substitute that part here. U minus r plus t naught, and dt becomes du. Then simplify this. So for simplification purpose, here I am writing like this, integration from minus infinity to plus infinity, f of u into, here write the separate exponential signals, e to the power of minus su, multiply this into du, and the remaining term is e to the power of this minus becomes here plus or minus. If you multiply with minus, it becomes plus or minus s t naught. Now observe this equation. Here the integration with respect to u is there, but this in this term u is not defined. That's why that part I am writing as it is, e to the power of plus or minus s t naught into, this equation looks like this equation here. See, Laplace transform of f of t is f of s, that is integration from minus infinity to plus infinity, f of t into e to the power of minus st dt. The complete equation defined with respect to t, that's why here f of t is there and here e to the power of minus st is there, right? And here also same thing here, f of u e to the power of minus su du. So this equation explains it with respect to u, that's why this is similar to Laplace transform basic mathematical equation, then it becomes directly f of s. See, finally Laplace transform of f of t plus or minus t naught is equal to e to the power of plus or minus s t naught into f of s, right? This property is also called as time shifting property. F of t plus or minus t naught is equal to e to the power of plus or minus s t naught into f of s. This is one of the important property, time shifting property, right? Whenever the shifting operation applies in time domain, then immediately we have to apply this property. Now here I will explain how to apply this property for different types of signals, right? For that purpose, first of all I am taking one basic problem here. F of t is u of t, otherwise let us write like this, k into u of t. F of t is k into u of t. Then find Laplace transform of f of t minus 2. This is one basic equation. So f of t function is there, then we have to find out Laplace transform of f of t minus 2, shifting applied in time domain. Then immediately we have to apply time shifting property. So from this statement directly I am writing now, Laplace transform of f of t minus 2 is, compare with this one. Here t naught is 2, constant value is how much? 2, and minus shifting is there, so delayed signal, right? So Laplace transform of f of t minus 2 is from this e to the power of minus s2, e to the power of minus s2 into f of s, into f of s. Now we want here f of s. What is f of s? Laplace transform of f of t is f of s. F of t is there, right? So just find the Laplace transform of this. Laplace transform of f of t is f of s. Then apply Laplace transform of this function. So already we have discussed. This is acts as unit step signal k into u of t. It is a step signal. Then Laplace transform of k into u of t, constant is k by s. Substitute that value in this, then you will get e to the power of minus 2s into k by s. K by s. So finally, that answer is here. Laplace transform of f of t minus 2 is e to the power of minus 2s into k by s. So to solve these type of problems here, time shifting properties applied, right? And one more example I am taking now. Find the Laplace transform of u of t minus 2. Now we want Laplace transform of u of t minus 2. U of t function is a unit step function. U of t function is unit step function. So unit step function amplitude is constant amplitude. That constant amplitude should be how much? 1, right? The constant amplitude should be 1. That's why directly I am writing like this. Laplace transform of u of t is 1 by s. Constant value how much here? 1 by s. And from this shifting property, Laplace transform of u of t minus 2. Laplace transform of u of t minus 2. So Laplace transform of u of t minus 2 times shifted. Then this side it multiplies with exponential function 2 times. So e to the power of minus 2s into 1 by s. Right? So to apply this property purpose, first of all we have to find Laplace transform of f of t or Laplace transform of the given function, and later apply the shifting property, then you will get the answer. So this type of analysis also important, because in real time application generally the available signals are delayed version signals, or sometimes the signals are advanced version signals, that means shifted signals. There immediately we have to apply Laplace transform, right? So please take this now.